Okay, you guys, welcome to day 2 of notes for chapter 26. I'm right now in my son Rylan's room. You want to see Rylan? It's 11 o'clock at night, and he's over here sitting in bed doing she. I don't even know what it sounds. I don't know. I don't know these things. So here we go. Here's your warm up. Go ahead, do it. Pause the video. Do the warm up. Okay, you've unpaused it. You've finished the warm-up. Now it's time for me to do the warm-up. So here's what we're doing. Here's the data for LAPD Metro Division's traffic stops in 2018. They showed you how many, the counts of how many people they pulled over of different ethnicities. And before 2003, in the Metro Division was ramped up. This was the percentage of drivers that they pulled over. 38% Hispanic, 33% Caucasian, 18% African American, and 11% other. Is there evidence that the Metro Division pulls over drivers at a different rate now compared with their historical averages? So, what we would need to do is take the total for your table here, and you're going to times it by the percentages, historical percentages. So 38% should be Hispanic. So you get your calculator, 59512 times 38%, right? You get 22614.56. 22614.56. You don't have to round it. You can use the decimal. So that is the expected number of Hispanic people that we pull over. And then 59,512 times 33% would be the Caucasian number of drivers. So 59,512 times your 33%, 19,638, 96. 19,638, 96. That's the expected number of Caucasian drivers. 638.96. And then 59,512 times 18% is the historical average on African American drivers times 18%. 10,712.16, 10,712.16. So 10,712.16, and then the other is 59,512 times your 11%. Put your other at 59,512 times your 11%. 6,546, 6,546.32, 6,546.32. So there are your expected numbers right there. So we could go ahead and remember we do not have to calculate this by hand. So hypotheses. So when you write your hypotheses, you're going to say we're trying to prove that there's a different rate now, so this would be that the rate is the same. Rate that Metro Division pulls over drivers is the same as in 2003. And we are trying to prove that the rate the Metro Division pulls over drivers is different now than 2003. So we're trying to prove it's different now. That's what we're trying to prove. That's our hypotheses, right? You would have checked your conditions. Your conditions were we had a random sample, so we can think about the rate that we pulled over as a random sample of people that are out there that get pulled over by the police in the Metro Division, and you had way more than 5. All expected counts are more than 5. So all expected counts are greater than 5, way greater. So we have a big enough sample by far. So there's your conditions, and then we can actually run the mechanics now. So this is the part where you use your calculator. We're going to go and run the mechanics. Let me scroll back up so I can see the numbers. So we're going to go to Stat, Edit, right? These are our numbers from yesterday. So I'm going to delete those, and I'm going to put in my new numbers. So 2,380 and 26,185. This is real data I pulled off of the LAPD website. So this is not made up. 29,161, 1,786. So they pulled over a lot of people in 2018. And our expected numbers from historical average, 19,638.96, 22,614.56 is our expected on that one. 10,712.16 is your expected on that one. 10,712.16, I put 15, and then 6,546.32 is your expected on the other. So we got your observed expecteds. Go to your test. This is your chi-squared goodness of fit test. You would write that name down on your test. L1, L2. How many degrees of freedom do I have? We had 4 categories. So 4 categories minus 1 will give you 3 degrees of freedom. Go ahead and calculate it, and boom, there's your chi-squared number. Holy moly. The chi-squared number is 50,000. That's the biggest chi-squared number I've ever seen. So chi-squared, goodness of fit. And we get a chi-squared number of 50,965.89, and then that gives you a p-value. The calculator almost never does this, but it gave us a p-value of essentially 0, and the degrees of freedom we already know were 3. So you write down all 3 of those numbers in your mechanics, and there's your point for your mechanics. And then your conclusion, right, will be that I definitely reject the null hypothesis because my p-value is essentially 0. We don't have evidence. No, we do have evidence because we rejected. We do have evidence. The Metro Division is pulling over people at a different rate over different ethnicities of people at a rate that is different than 2003. So they're definitely pulling over people at a different rate than they did in 2003 for the different ethnicities. If you look at your individual contributions of your chi-squared numbers, You want to see which cell is the most unusual. I think it's going to be obvious for most of you that African American is getting pulled over at a much higher rate than the statistical expected. So let's see, the chi-squared for the Caucasian group is 15,000. 563 for the Hispanic group, so that's not that far off. 31,000 is the chi-squared number for African American group, and 3,461 for the other group. So they are the farthest off on African Americans are getting pulled over at a much higher rate than we expect, and the Caucasian group is getting pulled over at a much lower rate than we expect. But the African American group is the most unusual group for pulling over. So what is going on in the Metro Division? I don't know, but it's worth a look because when you got a chi-squared of 50,000, there's something weird going on. Okay, something weird is going on. You can't establish cause and effect because this is an observational study, but you can definitely say that there is something weird going on and the data is not matching what we expect to have happen in that rate of pulling people over. So interesting. The Metro Division. Got to get internal affairs on the Metro Division to have them look at that data. Okay, so that was your warm-up practice problem from today. The new stuff was our two other tests we didn't get to do, the chi-square test of independence and test of homogeneity. If you need more time to copy these down and I go too fast, go ahead, pause the video anytime. I'm just trying not to bore people to death. If you're in period 2, I already did this yesterday, so period 2 you can sort of skip ahead a couple 5-10 minutes and you'll pick up where we left off. So these are the tests that we run when we have a two-way table. So a two-way table is when you somehow have more than one variable. I don't know how many rows you have, I don't know how many columns, but you somehow have more than one variable, like 9th graders, 10th graders, 11th graders, right? I don't know. And we ask you something about whether you drink or whether you don't, okay? I don't know, right? And we count up people, okay? That could be a two-way table, okay? Well, what the chi-squared test of independence is when you run the chi-squared test on one big sample. So one large sample was taken from a population and characteristics were recorded. And we would like to analyze or like to find out if the variables are independent. So if you have one big sample, that's the key on this one. You have one large sample and you sort of divide it up into the variables. So if I looked at all Westland High School students of 9th, 10th, 11th, 12th, I just took a big random sample and just asked people, what grade are you in? Do you drink? What grade are you in? Do you drink? And I just started recording little marks, right? And I would start to count up everyone. That's one big sample. I'm just looking at all the different groups. I would be looking at independence between the variables. Do the variables have some kind of effect on each other, or is drinking independent of what grade you're in? So that would be an independence test, whereas a chi-square test of homogeneity is very similar. The mathematics is the same, but instead of one large sample, we have multiple groups. That we analyze to see if their distributions are the same or different. So this one, you're looking for multiple groups on the homogeneity test. So typically experiments tend to be homogeneity because when you do an experiment, you randomly assign people to different groups. Like you have the COVID vaccine group, and then you have the placebo group that didn't get a COVID vaccine, right? And so we could compare them. That would be using homogeneity. So most experiments are going to be chi-square test of homogeneity. Most sampling from a big sample is independence. Sometimes sampling can be homogeneity if you somehow stratified your sample first. So you separated everyone by stratifying, and then you asked them about some characteristic or kept track of some variable. Then you're comparing the groups to each other because you made those stratified groups first, and then you're comparing them to each other to see if they're the same or different. That's homogeneity. So homogeneity, right, homogeneous. Are the groups the same basically, or are the groups different? Independence is you don't have multiple groups. You have one big group where we record different variables and you're looking to see if those variables are independent. So that's the thing you're trying to figure out is which test you're running of these two whenever you encounter a two-way table. So goodness of fit is not a two-way table. Goodness of fit is like just a one row thing or a one column thing where we have some distribution in counts. It's not a two-way table. Okay, so you know that that's not a other chi-square test because it's not a two-way table. So two-way tables are what you're looking for whether the independence or homogeneity. It's tough, you guys. Everyone every year has a hard time figuring out which test they're doing it. I've only gotten good because I've done it 6 years. So it just takes time. And you might get it wrong. And if you get it wrong, it's okay. You'll still get 3 out of the 4 points, even if you pick the wrong test. It's not going to like kill your grade on an FRQ. So here's the difference between the two tests. We have independence. The hypothesis on an independence test is that the variables that you're looking at, right, the variables are independent. That is the null hypothesis. We actually can't prove it. We're just assume it's true. You could also say that independence means there's no association, right? There's no association between the variables. The alternative is that the variables are not independent. That is what we're trying to prove. We're trying to prove there was some relationship between the variables, so there is an association. That's what we're always trying to prove. We can't prove they're independent. Okay, I can assume they're independent, but I can't prove it. I'm trying to prove they're not independent, which means there is an association between the variables. So those are what you write out. You write it out in words. It's not mathematical. You just write it out in words. I don't actually put the variables in the actual problem. I use context. What are the two variables? This one would have been um, drinking and not drinking and what grade you're in, right? So I would have said what grade you're in and whether you drink or not are independent. And then I would have said what grade you're in and whether you drink or not are not independent, right? Those I would write the actual variables in the hypothesis. For homogeneity, when you have the multiple groups, we don't write it like that, even though it means basically the same thing. We say the groups have the same distribution. So basically, right, we're assuming the groups are the same distribution. We're trying to prove the groups have a different distribution. So that's what we're trying to prove is that they're different. we're assuming that they are the same. Okay, so it didn't matter what group you were in, we had the same thing happen, same characteristic of the variables. So that's your homogeneity. Again, context. I'm not going to write the groups. I'm probably going to talk about what are the two groups, control group, right? That kind of stuff. So I'm going to put more context into it. The conditions are the same as the chi-square goodness of fit test, so you don't have to stress too much. We're not changing our conditions. You have a random sample. Uh-oh, Ryland's getting tired over here. I can tell. I'm trying to go as fast as I can. You have a random sample, or if you did an experiment, you did random assignment into the groups. Okay, don't get those wrong. Pay attention whether it's an experiment or a sample. And then you need to have all the expected counts are at least 5. Same as what we did on the goodness of fit. You do have to show the expected counts. That's the hard part. But we need to show that they're all at least 5. So the mechanics are the exact same mathematics. Your test statistic is your chi-squared number. And what are we going to calculate? How are we going to calculate the chi-squared number? We're going to take all of our boxes we have, and we're going to do the observed counts minus the expected counts, square that, and then divided by the expected counts. So that is what we're going to calculate. We're going to do that for every single box in the two-way table, and then we're going to add them all up, right? Because this just means sum. So you're just going to add up all those numbers, and you're going to get your chi-squared number, sort of like what we did on the goodness of fit. And then from that chi-squared number, we'll come up with a p-value. So we might use the chart or the calculator. And I'm going to be honest with you guys, I use the calculator. Oops, way too far down, way too far down. And then, oh, we need to write the degrees of freedom. The degrees of freedom on this one are a little bit different than the goodness of fit. It's going to be the number of rows in your table minus 1 times the number of columns in your table minus 1. That is going to be how you calculate the degrees of freedom. So like that table I gave you on the last page, 3 rows, 2 columns. 3 minus 1 would have been 2. 2 minus 1 would have been 1. 2 times 1 would have been 2. This has 2 degrees of freedom. So that's important, remember, because if you're trying to get your p-value, in order to know your degrees of freedom, you have to have calculated that before. Now, the calculator will do that one for you also. I'm pretty sure you won't have to do that one on your own unless you really want to. So there's your mechanics, and then your last thing is your conclusion. And your conclusion, remember, tell me your decision. Do you reject or do you fail to reject the null hypothesis? And then why did you decide that? Right? Why did you decide that? And use the p-value. And then make sure you have context. So this is where usually I will talk about my evidence to support the alternative hypothesis or not support the alternative hypothesis. So that's not changing. That's the same as we've always had on all of our tests in the last 2 units. So that's not going to change for you. Okay, so there's where we stopped in period 2. Period 1, now you know how to run the chi-square test. It doesn't really matter which one. You can see how you get 3 points, even if you pick the wrong one, because these 3 parts are all the same. So you could still get 3 points. You would just have the wrong hypotheses if you pick the wrong test. So who cares? Get a 3 out of 4. Who cares? That's great. If you get a 3 out of 4 on a chi-squared test, you did a great job. Okay, so what? You didn't get 4 out of 4. Doesn't matter that much. Okay, so let's do this problem. A random survey of autos parked in the student lot and the staff lot at a large university classified the brands by country of origin of the cars. Are there differences in the national origins of the cars driven by students and staff? Is this an independence test or homogeneity test? So we have two different basic lots, and they're looking at a staff parked lot. See, it said a student lot and a staff lot. So that right there tells me that this is more like two groups rather than them just ask random people on campus, oh, are you a student or staff and what kind of car do you drive? They just went to the two lots, so it's stratified by the lots, and then they looked at the two lots separate. So that's your clue right there that this is a chi-squared test for homogeneity or of homogeneity. However you want to say it, it doesn't matter that much. This is going to be a chi-squared test for homogeneity because we have multiple groups and we want to see if they're the same. And that's basically what they asked you. Are there differences in the national origin driven by students and staff? They asked you for are they the same? So the hypotheses will be the distributions are the same. The distribution of origin of car are the same for students and staff. That is your null hypothesis. And then you are going to try and prove that basically the distributions of origin of cars are different for students and staff. That's what you're going to try and prove with the alternative hypothesis, is that they are different. So there's that. C is check the necessary assumptions and conditions. Okay, so we had a random sample. It says it was a random survey. So we're good about that one. Random survey. And I don't like having the red. And over all of our expected counts, I don't know if there are at least 5. I haven't done them. So we're going to check. We're going to have to show that out. So this one we need to show, okay, but I'm going to show you how to use your calculator to get it. So I'm going to show you. The book goes through a long process of how to get it by hand. You guys, we're too late in the game to be worrying about how to get it by hand. You basically average the two groups together and you find like if they were the same, they would be the same. You'd sort of average them together and they'd be the same. So we don't have to do it by hand. We can use our calculator. So let me show you how to use the technology. This is how you're going to use your calculator. So this is the whole key part of this whole problem. So we need to be able to put this table into our calculator. There's only one place on your calculator you can put a table. That is a matrix. So it's been a long time probably since you've used this in advanced algebra. Matrix button is that x to the negative 1 button right there, and you see matrix above it. So you're going to hit second x to the negative 1. You're going to get this on your screen. Okay, names, math, edit. These are the matrices I've already made before, so they're already there, right? I'm going to pick A and B, so A and B are going to be the ones I'm going to use. So I'm going to go to edit, I'm going to click on A. And this is not a 2 by 2. This is 3 rows and 2 columns. So 3 by 2. And then all you're going to do is fill in the numbers from your table into this matrix. That's it. That's it. You guys, so really, your calculator is doing all of this work for you. 12, 55, and 47. So your calculator is doing all of it for you. You put it all in there. It's in matrix A. That's it. It saves it automatically. You quit. It's already saved. Now, go to Stat, Test. So write this down if you need to remember this. First, second, x to the -1, get to your matrix and edit. Put in your numbers. Then quit out of that matrix. Then hit Stat, Test, and go down to the plain old chi-squared test. And on this one, it's always going to say matrix A right there. Perfect. As long as you put your numbers in matrix A, you don't have to change anything. That is matrix A. We're always going to leave B there because that's where we're going to put the expecteds. It's going to put them in B. Calculate it. Boom. That's it. You're done. There's the test statistic. That's your chi-squared number for all those cells added together. There's your p-value, and there's your degrees of freedom. We had 3 rows, we had 2 columns. 2 times 1. There's your degrees of freedom. So you're going to write down all of those things. I've already written the name of the test up on the number right here. As long as you have the name written somewhere, you're good. So then right here, we're going to write down chi-squared equals 7.83. Doesn't seem too big, but it is big because the degrees of freedom were only 2. And so that meant that that chi-squared number was relatively big. And so that p-value was actually pretty small, 0.01996. So it's a fairly small p-value. So there's part E. Sorry, that was part D. I put it in the wrong one. Shame on me. Okay, so that should be part D. And then part E we'll put over here. And for part E, it says, what's your conclusion? You should put something like, well, I reject the null hypothesis because my p-value is less than some number that you decide. I say 0.05. I have evidence that the car origin is different for staff and students. So they obviously do not have the same. The only bad thing about doing it on your calculator is your calculator does not show you what each box is individually. That's the sucky thing, is the calculator won't show us how far off we are and what the chi-squared is for each one, like it does on the goodness of fit. Now, I told you in part C, the expected counts will be done for you. I didn't show you where to find them. So when you run your test, you have to first run the test. When you run that, it puts the expected counts in matrix B. So if I go click on matrix B and hit enter, you will see your 6 numbers here, and these are the 6 numbers that go with these, and those are the expecteds. So 115 was the expected for that one. 24.4 was the expected for that one, and 55.4 was the expected for that one. So you can sort of tell how far off each of those cells was from the expecteds. That European staff one seems to be much lower than we expected to be for European cars for staff. That seems to be the most unusual. But those are your expecteds. You would copy those down somewhere on your paper. You'd copy it down. Some people just write it right next to the numbers in the table. Um, I've seen some people do it like this. This is sort of fancy, but it looks sort of cool when people do it. If you had a table given to you, okay, this is what I want to show you. So if you had a table like given to you like this, and it had the three, here's what I see people do, and I sort of like it. It's a cool way to organize it. What some people do is they write down, they split the cells for each box with a diagonal, and they put the observed number on the top, and they put the expected number on the bottom. I sort of like it because it's a cool way to organize it. And what they'll do is they'll write in, like, this one is 107. And then the expected count for that box was 115.15, right? And they'll just do that. And so I'll get to see, oh, observed expected for each box. And you can really compare them very easily. So that's sort of cool when people write it that way. It's sort of nifty. It looks cool. Sometimes you don't even have to recopy it. Sometimes you can just, if you're on the AP exam, you can just write that straight on the exam. Now, you guys not as much because yours is a digital exam rather than paper. So you might have to write it down yourself. But you would need to show all of them. And notice they're all at least five. Look at me, I'm yawning. Even I'm getting tired. It's 11:40 at night. Okay, so they are all at least five. So you would just show it somewhere in your boxes. That's it. That's a chi-square test of homogeneity. If it was a chi-square test for independence, it would have been very similar to what we just ran on there. So the biggest thing is using your calculators on these chi-square tests for running the actual tests. I do not do them by hand. Okay, the calculator, the amazing thing is, right, your calculator can do matrices. You would have never thought that you could go and put your numbers in the matrix. And remember, you just got to go to edit and you can put in any size you want. You have a humongous table. Woo, there you go. Have fun. You got your humongous table. So it doesn't matter. Rows go first, columns go second. Um, yeah, it doesn't really matter. You can be whatever size you want. And then after you run the test, it will not do the expecteds until you run the test. So if you go ahead and put all your numbers in matrix A, and then you go back over here to the matrices, and you go ahead and click on matrix B, they're not going to be the right numbers in there because it hasn't run the test yet. You have to run the test first, which is backwards, but that's the way you got to do it on the chi-squared. You got to run the test first, and then you can go ahead and look at matrix B, and you'll see your expected counts, but you first got to run the test. So that's the biggest thing. Students forget to run the test. I'll be honest with you, when I grade these, students do not write down all the expecteds, and I don't see them, so I don't give you full credit on your conditions, and you get a half of a point on your condition. So make sure you put your expected somewhere on your paper so I can see them. And I know that you really weren't lying when you said they were all at least five. Um, that is it. We could see that 7.83 was fairly big. If you look at our stuff, if we look at our chi-square chart, you could have watched. Uh, you could have told that you were going to reject if you look at the table. Oh, wrong page. So if you look at your table here, we only had 2 degrees of freedom. The 5% number for 2 degrees of freedom is 5.99. Any number bigger than 5.99 for the chi-squared would have been unusual. This was 7.83, so obviously that was unusual. 7.83 was right around that area. So a tiny bit bigger than 2, so a tiny bit smaller than 2%. We got 1.99%. So there you go. It was a tiny bit smaller than 2%. So you can sort of have an idea of what this is by looking at the chart, but it's not exact. Your calculator gives you the exact when you run the chi-square test. So it doesn't matter whether you're running a chi-squared independence or a chi-square test for homogeneity. Everything is the same except for the hypotheses. That is it. That is it. So that's a long enough video. That's a 40-minute video, which gives you about 45 minutes to work on homework today. And tomorrow we'll go over that homework in class. So make sure you turn it in on time. We'll go over that homework in class. And then I'm still trying to figure out what we're going to do in the quiz. We might not have a quiz. I might just post a video of a quiz. I don't know. You might do a take-home quiz. I don't know yet. I don't know yet. Depends how good everyone does on the homework. So if you do a really good job on the homework and everyone participates in going over the homework on Friday, then maybe we won't have a quiz. So good luck. Hope you have a good day, and we will see you tomorrow with your homework done.